Hello everyone, this is Mr. Couple. This video is for my IB Physics SL Year 1 students. It's a continuation of the kinetic theory lesson from last week. So in our previous lesson, we derived the kinetic theory equation, which was 1/2 mc squared equals to 3/2 kbt. In this video, I'll be showing you working through some practice, like example problems, and then on the Google Classroom, you have 3 problems for you to practice on your own. So first, I'm going to walk you through these example problems, then you'll go answer those questions on your own, and I'm going to upload a second video that goes over the answers to those questions. Let's get started. So the first question here is explained with reference to the assumptions of the kinetic theory of gases why the internal energy of an ideal gas consists only of the random kinetic energy of its molecules. So this goes back to the assumptions of the ideal gas that we set out at the beginning when we derived the model. So the thing that we said was that the gas particles are extremely far apart from each other. So in an ideal gas, the molecules are far apart from each other and do not interact except for when they collide. So what this means is that there's no interparticle forces. So the particles aren't interacting with each other except for the physical contact that they make. So what this means is that there's no interparticle potential energy. So in an ideal, oh, I already forgot a word here. In an ideal gas, the molecules are far apart from each other and do not interact except for when they collide. Hence, there are no interparticle forces and thus no interparticle potential energy. And so that's why all that we care about is the random kinetic energy because there is no interparticle potential energy for an ideal gas. Now, obviously, that's incorrect for real gases. And that's one of the things that, our model is going to give us wrong answers. So you could say, like, you can estimate how a real gas would behave. So it's important that you know the limitations of the ideal gas model. Question 10. The temperature of an ideal gas is doubled at constant pressure. Determine by what factor the following quantities of the gas change. So we want to figure out if we double the temperature but keep the pressure constant, then how will the average speed of the molecules change? And how will the density of the gas change? All right, let's start with the average speed of the molecule. So we'll begin by writing down the Boltzmann equation, which we learned about last time. It was the equation we derived from the kinetic theory. So the result was that 1/2 mc squared is equal to 3/2 kbt. So on the left-hand side, we have the average kinetic energy, the average random kinetic energy of each molecule. And on the right-hand side, we have that relationship that's proportional to the temperature. Remember, K sub B is Boltzmann's constant. All right, so what we want to do here is we know that the temperature is doubling. So we've got twice as much temperature. So what we want to think about is, well, let's switch this over to a proportionality. The way you do that is you think to yourself, what are all the quantities that are constant? And just make all of those guys go away. And then we can replace the equal sign with a proportionality sign. So we'll think about this. So 1/2, well, that's constant, so that's going to go away. The mass of the molecules, that's not changing. We're just changing the temperature, right? So we're going to make the molecules, oscillate and move around way quicker. So the mass isn't going to change, but the speed is going to change, right? Because if you heat up the particles, if you raise the temperature, the particles are going to move faster. So C is going to stay there, but the 1/2 m doesn't stay. We're going to switch over to proportionality. 3/2, well, that's a constant. Kb, that's a constant. So the only thing over here that can change is the temperature. Now, what we know is happening is that the temperature is doubling, and we're wanting to find out how does the average speed, which is C, how does the average speed change? So if we take the square root of both sides of this relationship, we end up with C is proportional to the square root of T. And we know what T did. So what did T do? Well, it doubled. So I can write that as C is proportional to 2. So I'm just going to substitute my T with a double, because that's what happens when you're using the proportional sign right here. When we're using this proportionality sign, you plug in how quantities have changed rather than what they're equal to. So what does this tell us? This tells us that the speed of the particles will increase by a factor of root 2. Well, what is root 2? So we can put it in the calculator here, square root of 2. Square root of 2 is 1.4. So that means that the particles will travel about 1.4 times faster when you double the temperature. So it's not a linear relationship, right? A lot of people think that if you double the temperature, you double the speed, but it doesn't quite work out that way. Because remember, the equation is 1/2 m times the speed squared. Since the speed is squared, doubling the temperature, actually, you don't need to double the speed as well. You'll get a little bit less than double the speed, 1.4 times. So we'll say that the molecules move with square root of 2 times the original speed. And now we want to find the density of the gas. So this is going to be a little bit trickier because, like, what the heck is density? So before we get any further, I just want to make sure that we all remember that density, which is this symbol, which is the Greek letter rho, density is defined as the mass over the volume. It's the mass per volume. So it's like kilograms per cubic meter. So that's density. So it's been a while since we talked about density. And then also, we're going to need to think, well, where the heck are we going to get density? Because density is not in this equation. I mean, there's the mass over there, right? We've got the mass here, but we don't have volume in here. So we're going to have to realize that, well, we have another relationship that we can use, and that's the ideal gas law. So the ideal gas law says pressure times volume equals nRT. So what we'll notice is that we can find, from over here, the T, the temperature, can relate to the temperature here, and then the mass and the volume can get related to each other. So what we want to do is we want to solve this equation for T and solve this equation for T. If we solve both these equations for T and then equate them to each other, we'll have an equation with density in it. But let's make it a little bit easier than that. So what we'll do next is we'll just go ahead and solve this equation out for T. So if we solve this for T, we'll get T is equal to pressure times volume divided by the number of moles times R. And what we'll do is we'll substitute that in to the temperature over there. I think that'll be a little bit easier if we just substitute that in. So let's go ahead and do that. So we'll have 1/2 mc squared is equal to 3/2 kb. And then we're going to substitute in the temperature, PV over nR. And we'll do the same thing we did previously, which we'll do is we'll look for all the things that were constant, get rid of those, and the things that aren't constant, the things that we're trying to find that change, we're going to leave those in the equation. Now, what's different this time is that density depends on the mass. So while the density may be changing, the mass is not changing. So what's actually changing is when you increase the temperature with a constant pressure, then that means that the volume is going to change. But in order to get density out of this equation, we don't want to get rid of the mass. We want to leave the mass in there. So let's do that. So we're going to leave mc squared here, but we're going to get rid of the 3/2 kb because that's constant stuff. The n and the r, that's constant stuff. So we're going to end up with, oh, and p is also constant stuff. So we're just going to end up with v on this side of the equation. Now, we can get density, right? We can find the density by dividing both sides by the volume. And while we're at it, we might as well divide both sides by c squared. So I'll just show that that's what I'm doing. So I'm going to divide both sides by vc squared. And I do want to make sure that I say that this is, because it can get kind of confusing when you have volume and speed in the same equation. I mean, that's part of why we use c for speed, but I just want to make sure you guys don't confuse this with velocity. I'm going to divide both sides of this expression by v of volume times the speed squared. And you'll see what happens is the c squared just cancels out and the v cancels out. And so we end up with this expression that says the mass divided by the volume, which is the density, is proportional to the reciprocal of c squared. Be careful here because, yeah, the v's canceled, but that c squared is still on the bottom. V divided by v is 1, so we still have to have that 1 on top. Now, here's what we know. We found in the previous question that what did c do? Well, c increased by a square root of 2. So we can substitute that in here, 1 over the square root of 2 squared. Well, the square root of 2 squared is just 2. And so we can see that the density is going to decrease by half. So there'll be half the density. And that makes sense, right? Because if you're keeping the pressure constant and you're doubling the temperature, then the volume is going to have to expand. And so now the particles are going to be more spread out, and so they'll be a lower density. So we can just write down our statement here is that the density will decrease by a factor of 2. It'll be halved. It is very common in physics that you'll see questions like this where they're more qualitative questions, so you're not actually doing any calculations, but you're just looking at relationships between variables. This is one of the most important skills to have as a IB physics student, or just as a physics student in general, is to be able to reason and think things out through their interrelationships. Question 11. A sealed vessel at room temperature, that's 23 degrees Celsius, contains 5 moles of an ideal gas. Calculate the average random kinetic energy of the gas. Okay, so to find the average random kinetic energy, well, that's just the Boltzmann equation. So the E sub k, average kinetic energy, the over bar, remember that means average, is equal to 3/2 kb times t. So what do we need to know to find the average random kinetic energy? Well, we just need to know the temperature, because we can look up Boltzmann's constant in the IB data booklet. And I've got that out here right now. So here's Boltzmann's constant. We can see it's right here, and then that's just K sub B, and then here it is, 1.38 times 10 to the negative 23 joules per Kelvin. It's coming back to here, so I can calculate this. So the average random kinetic energy will be 3/2 Boltzmann's constant, I already forgot it, 1.38 times 10 to the negative 23, 1.38 times 10 to the negative 23, 1.38 times 10 to the negative 23, and that's joules per Kelvin. And that way, when you go to multiply by the temperature, well, you better not put 23 degrees Celsius in there, because what's going to happen? Well, the Kelvin and the Celsius won't cancel. And that's bad, because we need the energy to be in joules. So we know right away that you can't plug in Celsius to this equation. Remember, the units are really important, and they have a... What is going on? Why is everything getting deleted? What just happened? Are you kidding me? Hello? It's still deleting everything. What is happening? Okay, we had a little malfunction there, but it looks like I am back in business. So what we just talked about was that the units have to line up. So we have to, joules per Kelvin needs to be multiplied by Kelvin. So we need to convert this 23 Celsius, we need to convert it into Kelvin. So if you don't remember how to do that, the way you do it is you take 23 and you add 273. And so that gives us 296 Kelvin. So room temperature, so plus 273, room temperature is 296 Kelvin. So I just need to multiply this by 296 Kelvin, and then we're good to go. And so we calculate that the average kinetic energy, or I should say the average random kinetic energy, so we're going to have 3 divided by 2, and we're going to multiply that times 1.38 times 10 to the negative 23, and we're going to multiply that by 296. And we calculate that the average random kinetic energy of the gas molecules is 6.1, call it 6.13, 6.13 times 10 to the negative 21, and then the unit, of course, is joules. Okay, next question. It says, calculate the internal energy of the gas. Okay, so that's kind of strange. Didn't we just figure out the energy here? Wait, okay, hold on a second. The internal energy is the kinetic energy plus the potential energy. But since it's an ideal gas, there is no potential energy. The symbol we use for internal energy is capital U. So internal energy is the kinetic energy plus the potential energy. But the potential energy goes to 0 because it's an ideal gas. So realize that all we have to do is just take the kinetic energy, and that's just the internal energy. But it's a little bit more complicated than that, because this was the average random kinetic energy, and we want to actually find the total random kinetic energy is what we're looking for. So we're looking for the internal energy. So the way you do that is you basically have to take the number of moles and use that to determine the total amount of energy. So realize that this number over here, 6.13 times 10 to the negative 21 joules, that's the amount of energy that each molecule has on average. So what we need to do is multiply that times the number of particles that are in the sample. And the way to do that is remember that the total number of particles in the sample is the number of moles multiplied by Avogadro's number. We know the number of moles is 5, and then we just have to multiply by Avogadro's number, and that'll give us the total number of particles. So if we want to find the internal energy, we're going to need to take 5 moles times 6.02 times 10 to the 23rd per mole. That's molecules per mole. And then we're going to multiply that by the answer we had over here, 6.13 times 10 to the negative 21. 6.13 times 10 to the negative 21, and that's joules. And so you'll see that the moles and the per moles cancel out. Moles times per moles is gone, and we're just going to get joules. So all we have to do over here is take this number, multiply it by 6.02 times 10 to the 23rd, Avogadro's number, and then multiply that times 5. And then we get our internal energy of this gas. So the internal energy of the gas is, let's call that 18 kilojoules. So there we go. Okay, next question. Oxygen molecules have mass equal to 32 grams per mole. So that means if you have a mole of oxygen, it'll have a mass of 32 grams. Also, these are oxygen molecules. Oxygen molecules are different than just oxygen because oxygen molecules, they always come in two bonded together oxygens. It's a diatomic molecule. Find the mass of an oxygen molecule in kilograms. So this is somewhat related to what we were doing up here using this equation. But what we're going to say is we just want one particle. So N is equal to the number of moles times Avogadro's number. So what we're going to say is that if you had a mole, right, if you had a mole of oxygen, it'd be 32 grams. But what if you just had one particle? And so we're going to use this relationship to figure out the mass of a single particle, given that a mole has a mass of 32 grams. So let me write this out in a different way. So I'm going to write down that the mass is equal to, so we're going to have 32 grams. I'm going to write this in kilograms because that's the unit that we're supposed to use because it says kilograms. Excuse me. So to convert 32 grams into kilograms, I'm going to take 0.032 kilograms per 1 mole. But I also know that 1 mole is 6.02 times 10 to the 23rd molecules. And so now I'll have this in kilograms per molecules. So basically, I just have to take 0.032 and divide that by Avogadro's number, 6.02 times 10 to the 23rd. And now we have the mass of a single oxygen molecule, 5.32 times 10 to the negative 26 kilograms. I'm carrying an extra digit here because I don't want rounding errors because I know that I'm about to reuse this number in the next part. Estimate the average speed of oxygen molecules at room temperature. Okay, here we go. So now we're talking. So 1/2 mc squared is going to be equal to the average kinetic energy. I mean, I guess I could have written that a different way, but I just wrote it that way. So the average kinetic energy is 1/2 mc squared, where c is your average speed. But here's the trick, guys. We just, at room temperature, we just solved that problem. That was the previous question that we did. At room temperature, that was up here. We said that room temperature was 296 Kelvin, which means that this number right here is the average kinetic energy of the oxygen molecules. Because there's only temperature in here. So we would just redo this exact same thing. So we could just set this equal. We can just take that kinetic energy and just substitute it down there. And then we just need to plug in our mass of the oxygen molecules, and then we're good to go. So if we solve this for C, which is what I'll do right now, so solving this for C, what we're going to do is we're going to multiply both sides by 2, and we're going to divide both sides by m. Multiply both sides by 2, divide both sides by m. And then we'll end up with c squared is equal to 2 EK over M. That's EK bar, average kinetic energy. And so now we'll just go ahead and plug that in and see what happens. So I'll do that right now down below. So I'm going to write C equals 2, and I'm not going to write the squared because I know what I'm about to do is I'm about to take the square root of both these things. So I'm going to start plugging this in. So the square root of 2 times, now we're going to plug in our average kinetic energy, 6.13 times 10 negative 21. 6.13 times 10 negative 21 divided by the mass that we just found over here, 5.32 times 10 negative 26. 5.32 times 10 to negative 26. And we're just going to plug that all in there. So I've still got my mass right here. So I'm just going to take this 2 times 6.13 times 10 to the negative 21 divided by, and I'm going to grab that mass back again. What happens? Second answer. And then I'm going to take the square root of this answer. And I get 480. So the speed is approximately 480 meters per second. And you might be wondering, well, why did I have to say approximate? Why couldn't I just keep it as an equal? The reason why is because oxygen is not an ideal gas. So we're just estimating it by using the Boltzmann equation, because this equation only works for ideal gases. And so we're just estimating it as being an ideal gas. And so that's not the right answer, but it's close enough. And this is quite shocking. Like the particles, the oxygen particles, like breathe in. You just sucked in oxygen particles that had an average speed of 480 meters per second. That's pretty crazy. But, it's not that simple, right? Because what's happening is the particles are going to move and they're going to bonk into another particle and they're going to be going all over the place. So it's not like there's any one particle actually traveling that fast. It's just this random chaotic mess of particles moving everywhere with an average speed of 480 meters per second. Question 13. An ideal gas fills a container of volume V with a pressure P. Show that the internal energy of the gas is equal to 3/2 pressure times the volume. So that's kind of interesting because up here we found the internal energy by saying that it was just the number of particles times the average kinetic energy. So we'll write that down again down here. So the internal energy, so U is equal to N times the average kinetic energy. Well, the average kinetic energy is just 3/2 times Boltzmann's constant times the temperature. Yeah, that's correct. And now what we're going to do is do a boatload of substitutions. So the first substitution is that the number of particles is the number of moles times Avogadro's number. The second substitution that we'll do is that Boltzmann's constant is R divided by Avogadro's number. And then the last substitution we'll do is what we solved for T earlier using the ideal gas law, which is up here, PV over number of moles times R. So I can substitute in here that T is PV over number of moles times R. And if we do all these substitutions, we're going to end up with 3/2 pressure times volume. Let's do it. So first up is substituting n, which is little n times Avogadro's number. Next up, we're going to have 3/2 times Boltzmann constant, which is R over NA. And then lastly, times the temperature, which is PV over NR. It's really important to keep track of your big N's and your little n's. Okay, let's do this. So you can see that this number of moles cancels with that number of moles. Avogadro's number here cancels with Avogadro's number there. R cancels with R, and then sure enough, there it is. The average, not average, the internal energy is 3/2 of what's left over, PV. So that's a very interesting result, can be useful in certain situations. Let me give you an example. The picture shows a tank of compressed helium used to inflate a party balloon. Use the available data below to calculate the internal energy of the helium in the tank. We have the pressure of the helium in the tank. We have the volume of the tank. We have the temperature of the helium. Recognize that temperature? Yeah, that's just room temperature. 396, is it 396? 296 Kelvin. So if we want to find the internal energy, all we have to do is use that equation that we just proved. So 3/2 PV. So 3/2 times the pressure, which is 1.79 times 10 to the 6th pascals. I'm going to write pascals as newtons per meter because I think it's just it's going to make it a little bit easier to see that the unit actually ends up being the unit of the joule times volume, which is 1.6 times 10 to the negative 4 cubic meters. All right, so if we look at the units, which are important, newtons per meter times meters cubed gives us Newton meters squared. And a Newton meter squared, oh, it's not. A Newton meter is a joule. What's going on? What have I messed up? Newtons per, oh, because it's not a Newton per meter. It's a Newton per square meter. Remember, it's the force divided by the area. So I need units of force per units of area. There we go. So now we're good to go. So now the units end up being Newton meters. And a Newton meter is just a joule. So a Newton meter is a joule. And the way I remember that is because this is just work, right? A force times a distance is work. So that's a joule. Let's go ahead and solve this. So the internal energy, okay, so 3 divided by 2. And then we're going to multiply by 1.79. And I actually looked up these values for this actual helium tank like this. So these should be pretty appropriate to the real life values. 1.6 times 10 to the negative 4. Plugging all that in, getting my answer of 430 joules. Determine at what temperature the helium gas would have half the average random kinetic energy. So if at room temperature the energy was 430, then at what temperature would it have half as much energy? So that's what we're going to try to calculate now. Okay, let's see the best way to do this. So we'll think about the equations we have. So we know that we've got random kinetic energy and we've got temperature. Let me highlight this stuff. So we got this average random kinetic energy. We got temperature. So we know the equation that relates those two together because we did it up here. This one, the average kinetic energy related to the temperature. So I'm just going to write that same one down again. So the average kinetic energy is equal to 3/2 kBT. All right, so we're trying to figure out when it would have half as much energy. Well, realize that that key word there is that this is going to be a proportional change problem. So I could rewrite this equation as EK, average, is proportional to T, and then realize that there's a direct proportionality between the average kinetic energy and the temperature. So if we have the kinetic energy, we would need to also have the temperature. So this tells us that if you have the kinetic energy, you'd also be having the temperature. So we just need to figure out what half the temperature is. And then this is where it can get confusing because if you do 23 degrees Celsius and you take half of that, you're going to be way off the mark because you can't use Celsius. You have to use Kelvin when you're using these problems. So Kelvin is the absolute temperature scale. So what we really need to do is we need to say that the temperature will be half of the Kelvin temperature, which is 23 plus 273. And so if we find that temperature, it's just going to be 296 divided by 2. So it would, I just must have misclicked. 296 divided by 2. So we get 148 Kelvin. And the final question, calculate the ratio of the average speed of oxygen to carbon dioxide molecules when both gases are at the same temperature. Oxygen has molecular mass of 32 grams per mole. Carbon dioxide has 44 grams per mole. All right, so this is kind of similar up here. We're talking about the oxygen having 32. Now we're just going to say, hey, if the oxygen particles are moving at 480 meters per second, how does that compare to the speed that the carbon dioxide molecules will move at? So it's saying calculate the ratio of the average speed of the oxygen to the carbon dioxide. So we're trying to figure out how many times faster are the oxygen particles compared to the carbon dioxide particles. And we know that the oxygen particles are lighter than the carbon dioxide particles. So the oxygen particles should be moving faster because they're lighter than the carbon dioxide particles. So that's sort of what our intuition is telling us. Let's go ahead and calculate this. What we know is that 1/2 mc squared is equal to 3/2 kBt. We also know that they're being kept at the same temperature, which means that all of this stuff here is constant stuff. Also, the 1/2 is constant too. Obviously, 1/2 is constant. So what we can say is we can write this new equation, which says that mc squared is equal to constant. What this means is that whatever you do for m and c, if you do mc squared, you're going to get the same number no matter what, no matter whether it's oxygen or carbon dioxide. So we know that mc squared for oxygen has to be equal to mc squared for carbon dioxide. So the way we'll set this up is we'll write it as m of oxygen times the speed of oxygen squared equals to the mass of the carbon dioxide times the speed of the carbon dioxide squared. Oh, the subscripts are getting really gross here, but hopefully this is making sense. What we're looking for is the ratio of the speed of the oxygen to the speed of the carbon. So we need to get this, the mass of the oxygen over to the other side, and we need to get the speed of the carbon over to the same side as the oxygen. So what I'm going to do is I'm going to divide both sides by m oxygen of c carbon squared. So if I do that, the speed of the carbon moves to the other side, and then the mass of the oxygen moves to the other side. And so we end up with this expression that says the speed of the oxygen squared divided by, you know what I'm going to do is write this out as the ratio of the oxygen to the carbon dioxide squared. So I'm just taking that down there and just pulling the squared out is equal to the ratio of the mass of the carbon to the mass of the oxygen. So now it's very clear to see that if you want to find the ratio of the speed of the oxygen to the speed of the carbon, you're going to have to take the square root of both sides of this equation. So I can say that the ratio of the carbon speed to the, of the oxygen speed to the carbon speed is simply this mass ratio, which we know for carbon is 44 grams per mole divided by 32 grams per mole. And I know that I just have to take this whole thing to the 1/2 power because 1/2 power is the same thing as square rooting it. I just think it'd be easier to write it as 1/2. It just seems like it looks nicer that way. We'll notice that the grams per mole units will cancel out because we're dividing them on top and bottom. And so we just have to figure out what 44 divided by 32 and the square root of that is equal to. And we get this as our answer, 1.2. The speed of the oxygen compared to the speed of the carbon is equal to 1.2. So what does this tell us? It says that the oxygen, so we could finally write this out like this. We could say that the speed of the oxygen is 1.2 times faster than the speed of the carbon. And so that's our ratio. It's 1.2 times faster. Okay, that's it, guys. I'm going to post, I should say I have posted questions on the Google Classroom. Go check those out. And then I'm going to post a second video for you to watch after you've answered those questions. All right, I'll see you guys later. Have a great day.